So,
Hey,
hello, Alexander. Yeah,
yeah.
it was. Yeah,
Can you hear me well?
yeah, we can hear you. We can hear you. At least I can hear you. I assume others. If I can hear you, probably others also can. But if somebody has issues, please. Somebody have issues. Please write in the comments so we know that we are experiencing some difficulties. So I'm yeah we are heading to the stage of the presentation, and yeah, the topic is cross-chain proof of membership. Oleksandr Kurbatov from Distributed Lab. Alexander, the virtual stage is yours.
Okay, thank you so much. I hope you see my screen right now, or not yet. Okay, I assume that yes. So
Yeah, we see your screen. Yes.
okay, that's fine. Yeah, my name is Oleksandr. I am lead of cryptography and research at Distributed Lab, and at the same time, I am receiving a PhD in cybersecurity. So yeah, we try to solve like a really simple problem. It sounds problem, but like on the practice, it's not so like easy as it sounds. And we tried like to build a prototype for cross-chain proofs of membership. I mean, like the situation when you particularly can have a separate accounting system, and the first system can account some like whitelists. This whitelist could be organized by different ways. So it can be some like NFT owners. It can be some array with allowed participants or something like that. It doesn't matter. Only like the first blockchain, the first one accounting system includes the list of allowed participants, the list of allowed external owned addresses. The next one, this is like consumer system. It also can be blockchain based. And the goal of the second system is storing some proofs and verifying these proofs. And these proofs can be connected to different things. For leaving some anonymous feedback, for providing some service, for like timestamping some like actions or like events, something like that. But like the main goal, it's like provides a way to properly verify of the second system proofs that is generated based on some state on the first one. So yeah, you know that the majority of platforms regulate the access of users based on some whitelist. As I said before, this whitelist can be different. But in our example, we will be managed by some NFT contract. So it can be ERC-721 contract, and just we assume that this contract can provide to you the list of NFT owners. So yeah, for traditional systems, it's not a big deal if the following set of rules is like provided, is set. So the first one, the whitelist is formed and managed internally. It means that if your accounting system allows you to provide some like administration internally and allows you to form this whitelist internally, you will have no problems. The problems you will have if this whitelist is generated by external party. In this case, you should like transfer this data from the external system to the to your own. As next one, access is provided based on authentication mechanism native for the system. Under the hood, we will presume that all like every good system should provide you the ability to verify your actions using digital signature. So we are not talking only like about blockchain-based accounting system, like any secure and any protected systems should allow you to do something based on digital signature in some kind of public infrastructure. And the last one, the privacy of users isn't provided. So yeah, for example, if you register it in some system, if you have account in the system, yeah, definitely you can do some action and like the permissions that is connected to your account will be verified by the public key. But in this case, the validator or like the site that should perform some transactions or operations or something like that, they will know who exactly did something. And if you are going like to achieve some privacy, you should use like other options, and today we'll talk about them. So if the system wants to provide access based on the external whitelist and anonymously, sometimes it's very difficult to implement, especially when like the consumer system also is blockchain based. So you need to implement this verification logic on chain. And usually for that, you can use smart contracts. So yeah, let's provide example, and we have built a prototype for this example. So let's imagine some marketplace, and there are a list of there is the list of conditions. So there are some marketplace based on the separate accounting system. So just imagine that this marketplace is a private fork of Ethereum, So it's based on Ethereum virtual machine. It can have some like consensus reaching mechanism, but with like permission in some permissioned environment. The next one, marketplace integrates a lot of product seller. So yeah, like Farfetch, like different other marketplaces. So they are aggregators of different sellers, of different I don't know, product producers, and that's it. Next one, each product seller, each product creator, they issue NFTs to their consumers after product purchase. Just imagine that you bought something, and you should have some proof that you bought this thing. For example, you can show that to someone. For example, you bought some like Rolexes, and later you can prove that you bought that without like showing them to everyone. You just can show NFT, and everybody can be sure that that's true. So yeah, for organizing some like consumer business relationship, we can use some like tokenized asset and in our example, that's NFTs. So yeah, and there are two conditions. The first one is obvious, that marketplace can't issue this NFT because a marketplace isn't like initial product producer, and so business is interested for organizing this relationship with the final consumer, not with marketplace, not with like third party. If you bought something from Nike, from I don't know Rolex, from something like from Mercedes, they should have a connection with the final consumer. They should have their own user base. So obviously, marketplace can produce these NFTs. It should be issued directly by the product creator. And the next one, sellers issue these NFTs on any network they prefer. So you can push them to issue NFT only on like some preferable network. So you can say, okay, you should issue these NFTs only on Ethereum, only on Polygon, only, I don't know, Polkadot, only on Bitcoin. So it doesn't matter. They will decide themselves how exactly and where exactly they're going to issue these NFTs that confirms their relationship with consumers. But marketplace wants to provide the ability to leave a feedback about the product. It means when I use the traditional marketplaces, I'm not sure that feedback was left by authentical consumer. I'm not sure that some bot didn't leave this feedback, but if these traditional marketplaces provide this ability, they will know who exactly left this feedback, because they don't provide you different tools for achieving privacy of end consumers. So we are in the angle, and we should resolve the following problem, where you can leave some feedback on the second chain. The second one, you should do that anonymously. And the third one, everybody should be sure that only the authenticated user, so only the user from allowed list, left this feedback. Okay, so there is not a simple but pretty clear scheme that there is a user, there is the system number one, where initial NFTs were issued. There is system number two, this accounting system of the particular marketplace, and there can be some verifier contract or verifier module that should consume some proofs verify these proofs, and like timestamp the feedback that left by the particular user. There definitely should be some Oracle. Oracle is a party that transfers the data from one system to another one. It can be centralized, it can be decentralized, it doesn't matter. And the last one, that's a client. So by the client, I mean some like applications, some softwares that can generate these proofs properly and can send that to the like target accounting system. So yeah, we try to implement that via 3 ways. So the first one, you can use Zika circuits and private key directly for proving that some user is included in allowed list. So allowed list consists of the list of public keys, not public keys, but addresses. And so the private key should be source from which some of these addresses was generated. And you can like add this construction to the circuit and prove that some particular public key, some particular private key derives some public key and address, and this address is included in Merkle root of the like final like I don't know timestamp for final state. The next one is like old school example. That's a ring signature, so you can use approach like in Monero for like creating these proofs. And the next one is using ECDSA signature in circuits and provide like the proof that the public, the some address belongs to some signature that is provided as a private input, and that's correct, but without revealing which digital key is used for verification of the signature. So yeah, let's go through these examples. The first one is like the simplest model. We are not talking about like the key constructions, not about like gross extent scheme, etc., etc. So in the first example, we use private key and Zika circuits.
Alexander, my apologies for interrupting. Please continue, but just be aware that the paper presentations are limited to 15 minutes with questions.
Okay.
They're not like keynotes. Yeah.
I have only like 9 slides or 10 slides, so it will not take a lot of time. Okay, yeah, thank you. So yeah, in the first case, we have some circuit, and so we have like 2 private input in the circuit and 2 public ones. The private key and Merkle branch. The public one, the message hash and Merkle root. Yeah, so that's like the simplest model what we can to implement, but it so you can see that verification cost is not like not much. Proving time also like the small. The proven key like not so small, but anyway you can upload that to your web browser, to any application, so it shouldn't like be a big deal. But there are some disadvantages. The first one, you should provide the direct access to the private key. And right now, not all wallets allow you to reach private keys and use them for like different crypto algorithms, for using them for different schemes. Yeah, so for example, for MetaMask, you can use MetaMask snaps, but not for all wallets you can use that. So that's like user experience, some difficulties, and so that's not a totally user-friendly model. The next one, ring signatures. Yes, shortly, the verification of the signatures is pretty difficult by the smart contracts, so you can use that ever if you have only 3 signers. Like the verification cost will be like really high, and you will like spend a lot of money for verification of this transaction on some public network. But this scheme no require trusted setup. It can operate only like with public keys and signature. But there are the list of disadvantages. The first one, yeah, expensive on-chain verification. So if, for example, you have the backend that should verify that, it will not affect on the cost and something like that. And it will be like really fastly. But if you're going to perform the verification on chain, you should pay for that, and you will pay a lot. The next one, you need to store the full list of addresses. So in the final contract on the destination chain, you should store not only like some Merkle proof, but all list of public keys or probable public keys. Like you also should pay for storage these keys in this contract. And the last one, it's impossible to receive the public key for particular address if no transaction sent before. So if, for example, the product creator sent the NFT to your account, but you did no transactions before, it means that nobody can recover your address from the signature, and nobody can recover the public key from a CDSA signature. And it means that this scheme for some like cases is unuseful. And the last one, it's like more a user-oriented scheme, but like pretty, I don't know, heavy. That's like the CDSA signature and the gas circuits. But you can see that number of constraints. This like parts of ZK program is like really huge. And it requires a really like big proven key for verifying, for generating these proofs that can be consumed by the verification contract. And it's obviously that almost 1 gigabyte can be uploaded to your web application. It's very non-usable by the user, etc. But verification is not so like expensive, and proven time also the small. The main reason is like the CDSA curve supported by Bitcoin, but by Ethereum, etc. That isn't ZK friendly. It means that you can't do official computations with this. With these keys. And let's briefly see on the comparison of existing solutions. So there are like 3 famous realizations. The last one is our, for Spartan ECDSA, it's like consumes. It requires the minimal number of constraints, but it uses the separate curve. So that's not compatible with Ethereum, with Bitcoin, etc. There are 2 implementations of efficient ZK ECDSA and Circum ECDSA. They consume less gas. They provide less constraints that, for example, our implementation, but they requires setups. They require some preliminary computations. And this computation should be provided by somebody. Usually this like some centralized party. In our case, you can verify that on chain, but this kind of it can be like more efficient with precompiled contracts. But you can use it directly, but with like high key, with a large key, as we discussed before. But it's possible. Okay, that's it. Later we are going to do some experiments with Starks, and we are going to build the prototype of the solution top on Stylus. It's like Arbitrum-based protocol that allows you to create a set of precompiled contracts and write different contracts using Go and Rust languages that probably can provide more efficiency in computations of all these constructions. Okay, thank you so much. Feel free to ask any questions.
Thank you, Oleksandr. So there is a question, but first the most important basically the most important announcement to 2 speakers which are going after you. The paper presentations are limited to 15 minutes. They are not the same as keynote speeches. So tomorrow you will have 30 minutes keynote speech, and 2 following presenters, I kindly request you to try to fit into 15 minutes slot with with questions, because we are already having speakers who are waiting their time to speak right now. Oleksandr, I had a question to you regarding the implementation of this. Basically, how it is limited to networks? Does it work for only Ethereum-inspired network, or does it work only for networks which enable smart contracts, or does it work for networks which enable something else? What are the requirements?
Okay, yeah, in theory, it can be implemented on any network you prefer, but yeah, it makes sense to test that on like existing network, because yeah, this should be like some kind of applied for end users, and there is like anyway you have some limitations. These limitations can be like a block size. For example, in Bitcoin, these limitations can be in gas amount of gas that can be consumed within one block. That's like limitation for Ethereum. That's the reason why you can't realize bulletproofs based on Ethereum, because it consumes more than probably can be included in one block, etc., etc. So if you have some backend part, centralized backend part, it doesn't matter which scheme you're going to use. But yeah, it will be verified by the centralized party. If you are going to create some on-chain proof, you should select the technology properly, because sometimes you can use everything. You should like spend a lot of time for selecting the right methodology, the right approach for generating like these proofs. But yeah, we tested that on Ethereum, on testnet of Ethereum, because yeah, on Ethereum.
Yeah, well, 80% of the major chains supports Ethereum. So yeah.
Yeah, a lot of like built based on Ethereum virtual machine. So there are a lot of developers. There are a lot of products. So it makes sense to build that with Ethereum smart contracts.
Got it. Thank you so much for this great presentation. We are forced to move to our next paper presenter, and we look forward to seeing you tomorrow giving the keynote speech.
Thank you, Tom. Yeah, have a nice day. Bye.
Thank you. Bye-bye.